Swayam Prabha. Digital India. Educated India.
All right, welcome everyone. So let's continue the discussion. Today we'll start looking at some candidates for post-quantum cryptography. So we have spent a lot of time developing and understanding, what kinds of problems underlie cryptography, right? And this is actually a rich theory in itself. I think the tragedy of a course like this is that, it has connections to so many really interesting and deep fields, but we have very little time to spend on any one of them. So necessarily, we are having to look at many of these things in a slightly higher level than what I would have liked. Anyway, so today we will start talking about some of the candidates we have for post-quantum cryptography, right? And the idea here is, just to find candidates for mathematical problems that are hard to solve even for quantum computers. So this is one of the really cool things about cryptography is it's, like there is this saying, right, that if life gives you a lemon, make a lemonade, right? So as computer scientists, we want efficient algorithms for everything or many things. And seen from a distance, one can understand that we have efficient algorithms actually for very few problems. For most problems, we really don't know how to solve them. But cryptography says, oh, that's not a bug, it can also be a feature, right? So we use these hard problems to get something useful. And now, of course, we are moving this philosophy to the quantum setting. So we would love to have quantum algorithms for, a large number of problems, but we don't. And now we'll again use this to our advantage, right? So we will try to find problems that are also hard for quantum computers. I mean, this rotate, compute, rotate, at least it seems to have, only so much power as far as we understand right now, right? So unless there are fundamental breakthroughs in quantum algorithms, we expect some of these problems to remain hard, and we will develop our cryptography using that. Okay. So lattice-based cryptography, this is a topic that I actually teach a full course about, and it's very rich and it has a lot of really interesting math, really interesting ideas. As I already said, unfortunately, we'll have to do very little of it in this course, but let's do what we can. So today's class, I'll try to present a slightly high level overview of some of the ideas that we will use in lattice based cryptography. And my plan is to delve into one particular application in detail. This is the application of fully homomorphic encryption. We will not get to it today, we will do it next class onwards, I hope. But today's class we will try to get more an overview. Okay. Okay, so first of all, let's start by defining a lattice. Okay, so what is a lattice? It's a periodic arrangement of points. Now lattices are very old mathematical objects, they have been studied for centuries. They occur naturally in nature. What's an example of a lattice that you've seen in nature, like a periodic arrangement of points? Crystals, very good. Crystals, snowflakes, beehives, piles of fruit, right? So they really occur everywhere. And of course, that is as you would expect, because mathematics is really abstracting phenomena, right? So a lattice is a periodic arrangement of points, and the simplest lattice mathematically that we can think about is just the integer lattice. So just take integers, right, high dimensional, so z to the n, for instance, so n dimensional integer points. Okay, this is a lattice. The basis vectors are also familiar to all of you. So just the unit vectors, right? So 1 followed by all zeros, 0, 1, all zeros, and so on. It's very easy to see that this will generate all integer points, right? But of course you can generalize the idea, right? So it doesn't just have to be integers, and that is where the fun begins, right? So other lattices can be obtained by applying a linear transformation to this integer lattice. So we'll use lambda as the notation for our lattice, and we'll say that lambda is b times Zn, okay. So for some b, now b here actually can be real, it can be, it does not have to be integral. This matrix B can be over the reals. So basically a set of points with a periodic arrangement at a very high level, a discrete subgroup of Rn is a more formal complete definition, okay. We will think of lattices in terms of their basis vectors. So now starting to get a little more formal, a lattice is the set of all integer linear combinations of these basis vectors b1 to bn, okay. So think of just exactly what we said, right. So just taking sort of summation ci bi, where c are integer points, okay. So you can see here, right. So basically bx where x is in Zn, this is a lattice, and the same lattice can have many possible bases, okay. So you can get one basis from another basis by applying a unimodular transformation. We'll get to that maybe. So right now we'll just say that it's very natural, right. So you can have many different bases for sets, and this is one of. So as I was saying, we'll define some interesting quantities on lattices, and these will be quite central to the hard problems that we will define on them. So a very basic quantity in a lattice is, what is the length of the shortest vector. So now any lattice has the 0 vector in it, and you could ask what is the shortest non-zero vector. So now in general, for a small toy lattice of the kind that we are showing here, these 2-dimensional lattices, it's quite easy, right. So what do? I mean, you just maybe try to enumerate the points around the origin, and you can measure and see which is the shortest one. But as your dimensions grow big, right, this will take exponential time in the dimension, okay. So yeah, so that is a very basic problem in a lattice, okay. So a little bit more formally, we are going to define the minimum distance as you can see here, right. So the minimum distance between two lattice points, so it's the minimum over all x y in L x not equal to y, norm of x minus y, right. And because you have 0 in the lattice, this translates as the length of the shortest non-zero vector, yeah. And now this is my minimum distance in the lattice, okay. So this is the shortest, the length of the shortest vector. I can define successive minima. This will turn out to be important. So what are the successive minima? As you could imagine, it is sort of the lengths achieved after the shortest, right. So what is the second shortest length, third shortest length, and so on. One needs to be careful in how you define these formally. So the right way to define it is as we see here, right. So lambda I is the minimum R such that the dimension of the span of ball R intersect lattice is greater than equal to I. Let's decode this, okay. So what is this saying? Basically, let's look at this ball. So as you can see this red colored ball in the picture, right. So this I'm think of growing a ball from the origin, okay. Now when I hit my first lattice point, the radius is lambda 1, okay. Now I will continue growing this ball until I hit the second lattice point. But now I have to be careful that the second lattice point that I hit is not that it is linearly independent of the first one, right. So basically I want the dimension of this space. So let's look at the lattice, okay, intersect with the ball. So let us look at the points in that, right. I want to count the second distance, the second shortest distance as being achieved by the point which is adding to this dimension. So when I hit the first point, right. So let us look at this point, right. Now what is the ball intersect the lattice? I mean, it has in this picture, you know, this point and this point, right. So I have these points, right. Now I am looking at the dimension of this set, right. And I want to define my lambda 2 as being achieved by the next point which is not spanned by the points that I have already discovered. Does that make sense? Okay. Yeah, it's clear to everyone. So this is the formal way of writing it, and it is exactly as we said. So you keep growing this ball until you hit a new point that is not spanned by the old points. So you want the dimension to keep growing, okay. So this way we will define our successive minima. So you can see in this picture here, right. So this is lambda 1, right, and lambda 2 is here, right, and lambda 2 here is not in the same line. So it is not here, for instance, right. So it is it is not spanned by the point already discovered. So in Zn all the lambdas are just 1, okay. So n is the dimension of the lattice, right. So if your question is what happens if all the points are in the same on the same line, in that case what is the dimension of the lattice?
Because it is 2-dimensional.
Sorry, the point is that you will not have many lambdas all on the same line, right, because in the case where all the points are on the same line, your dimension itself is small. So okay, so in that case you will just have a lambda 1. So if you just have all these points, right, then this is just a line. So this is just one dimensional. So I cannot infinitely keep defining lambdas by just growing this ball. Every time I hit a new point I get a new lambda. No, the dimension of the space has to increase. Okay, so we defined our lambda 1, right. So let's define the most classic problem on a lattice, which is the shortest vector problem. So the shortest vector problem is the problem of finding the shortest non-zero vector in the lattice. Okay, so what is the point in the lattice which actually achieves this lambda 1? Okay, and note that this problem is interesting or non-trivial because the basis vectors could be arbitrarily long, right. So you can see here in this picture that my b1 and b2 are these big long vectors, right, and my lambda 1 is being achieved by some combination of them. So 5b1 minus 2b2, right. Okay, so yeah, this is the shortest vector problem, and in computer science it's interesting to define approximate versions of these problems. Okay, so particularly for cryptography this will turn out to be quite important. So we are trying to do something useful with the hardness of these problems, right, and it will turn out that even solving these problems approximately can be very useful for cryptography. Okay, so the approximate shortest vector problem is to relax the constraint of finding the point that achieves lambda 1 to simply saying that let there be some multiplicative factor gamma, and I am interested in achieving a point that that has length up to gamma times lambda 1. Okay, so if this inner ball is lambda 1, Okay, I can define an outer ball which is some gamma times lambda 1 and say that finding any point within this is fine. So, this will not have a unique answer, right, it could have many possible answers, any one of them if you find, it is a solution to the problem. Okay. Now, the next very famous problem on lattices is the closest vector problem. So, the closest vector problem is that I am given a lattice in terms of its basis and I am given some arbitrary point in space. Okay. So, some t, so some target point t that we see here, and now we are trying to figure out which is the closest lattice point to this point. Okay. So, yeah, so now we'll give some parameter mu and we'll say that find me a point in the lattice which is at most distance mu to this target point. Okay. This is the closest vector problem as the name suggests. And once again we can define an approximate version of this where again we relax the mu to some gamma times mu. There is a lot of very rich theory around these things. I mean what are the sort of most interesting ways of solving these problems. There is a lot of algorithmic theory around how to solve these problems in the most efficient way. Right, and there is also a lot of very interesting theory about how these problems relate to each other. Like if I have a way to solve one of them, does that imply a solution to another one of them? If so, then with what loss? Like if I can solve the approximate CVP for some gamma, then does that imply a solution to SVP for some other gamma prime? If so, then what is that gamma prime, right? So, there is a lot of interesting theory around it. Okay. Now, the third classic problem is the shortest independent vectors problem. Okay. So, here as the name suggests, you are interested in finding points that achieve approximately all the gamma I that we defined, lambda I, sorry, all the successive minima, right. And again we will have a shortest an approximate version of it. So, given a lattice, right, represented by its base is B. So, what I get in my hand is B. The question is to find n linearly independent lattice vectors Bx1 to Bxn of length at most gamma times lambda n. Okay. Okay, good. So far so good, right. So, we defined a lattice, we defined some interesting problems. These are, like I said, the very classic problems on lattices. These it turns out are actually not very directly useful for cryptography. So, what I mean by that is that these problems do not have the kind of structure that I can start building crypto systems from them. These are what are the underlying hard problems. What we will do for building cryptography is, we will define some other problems, we will relate them to these, okay, and we will build crypto from that. Okay. So, how do these lattices get used in cryptography? So, first of all, what are the kinds of lattices that we use or consider in cryptography? So, a lattice, the definition I gave you is very abstract. Right. So, it's this it's this integer linear combination of a bunch of basis vectors. Now, if I want to use such a thing for cryptography, then I need to also generate some useful lattice, isn't it? So, remember, like when we have seen for instance the RSA crypto system, there is also, you have to think about how to generate the modulus, right. So, in cryptography you need a constructive approach, right. So, what is the lattice that we will use? By the way, this is a very serious question, right. Like what is the lattice to use is a very serious question, because it does not suffice to just choose some lattice. For instance, why should not I just choose the integer lattice if if my only concern is to have a lattice that I can sample efficiently, right? Then why shouldn't I just use the integer lattice, because problems on that will not be hard. So, as usual, right, I need this balance between efficiency and hardness. I need to be able to sample efficiently a lattice on which I can hope that the underlying problems will be hard, because these problems which I showed you, I hope that it is clear to everyone that these problems are not hard by definition. It depends on the lattice, isn't it? So, this is in a way the, I do not know, blessing or curse of computer science, right. So, we have worst case hardness. We understand worst case hardness for many problems. What we need, at least for cryptography, is average case hardness, which is to say that, you know, there should be an efficient way to sample an instance of a hard problem. Only then can I hope to do cryptography with it. Okay. So, what are the efficiently sampleable lattices that we will use for cryptography, which, you know, we believe to have hard problems, believe to have hardness. Okay. So, these are these so called query lattices. Okay. So, cryptography typically uses random lattices such that you know, the lattice lambda is an integer lattice. Okay. It is an integer lattice and it is periodic modulo some small integer q. Okay. So, these are these query, what we call query lattices. So, these lattices only involve arithmetic mod q, alright. So, here is the definition. A lattice lambda is a query lattice if q times zn is contained in lambda and lambda is contained in zn. Okay, this is the definition of a query lattice. And the two lattices that we will be most concerned with are the following. Okay, let us take you know, a matrix A in ZQn cross D. Okay. And let us define these two lattices. So, one is you know, what we call lambda qa. This is the set of all vectors x in you know, z to the d, such that x can be written as A transpose an integer vector. Okay. So, basically think of the first lattice, think of it as being you know, generated by the matrix A. You can think of A as a kind of a generator matrix. Okay. So, if I take you know, A transpose an integer vector, right, then I will get you know, integer linear combinations of the rows of A, right, and that will give me the points in this lattice. Okay. The other one which is very useful is the so called perp lattice. Okay. So, the first one is you know, where we think of A as a generator matrix. The second one is where we are not thinking of generating points using A, we are thinking of the kernel of A. So, we are looking at points, right, that are annihilated by A. So, we are looking at points x such that A times x is 0 mod q. Okay. So, these are the two lattices that we will be most concerned with.